Hello guys, we're going to solve a problem now on laterally unsupported behavior. So this is an example in the book of Segi. So we are asked to determine the flexural strength of a W14 by 68 A242 steel subject to the first is using a continuous lateral support. Second is using an embrace length equivalent to 20 feet. And the third is using an embrace length equivalent to 30 feet. Both B and C assumes that CB is equal to 1.0. So for an A242 steel, which is not quite common to us, we simply refer to AISC manual on the table 2-3 in part 2, wherein the minimum yield strength is actually a function of the flange thickness of the section, which is 0.72. So the yield stress is based on the flange thickness, and this corresponds to a value of 50 ksi, which we are going to use for this particular problem. And an A242 is a steel design to resist some corrosion attack. So this is normally used for a high acidity environment, such as those exposed to salt water, okay, and also on structures which are used to support or are exposed to chemicals. So we can use special type of steel, which is A242 in that regard. So the first thing we have to take note is to find the property, from the table. So we collect the needed properties, or extract the a property given from the table. This is W14 by 68. And these properties are needed not to facilitate the computation. In fact, other tables, AISC tables, are so complete that special properties such as x1, x2, and LPs and LRs are included, in the table. So for this particular table, those properties are not available for us. So we need to compute for such properties. So to begin with, we check on the compactness requirement first. Although the probability of having a compact section for AISC shapes are very high, especially on web. Still, we need to check it for assurance that we don't have any problems regarding compactness. So the values for the checking we need are the modulus of elasticity, which is in 29,000 ksi, and Fy is equal to 50 ksi. So for the flange local buckling, we simply compare your width to thickness ratio Bf over 2Tf, which is 6.97, with that of the lambda p, okay, the lambda p limitation. So this can actually be uh, obtained from the table, which is 6.97. Computing this for values of E and Fy given, so we can see that this is less than the limit, therefore the flange is compact. So for the web local buckling, we don't need to check this actually, because web is always compact for all shapes in the AISC manual for Fy less than or equal to 65 ksi. But for purpose of presentation, we simply take the value of h over tw from the table, okay, and compare it with the lambda p web limitations, which is 90.553. So take note that this is very much less than the limit, therefore again the web is compact. So for the continuous lateral support requirement on the first condition given in the problem, all we need to compute is the value of your plastic moment from the formula ZXFY. So this 12 here is for conversion purposes from inch kip to foot kips. So ZX is from table, which happens to be 115 inch to the inch cube multiplied by 50, you get 479.167 cube foot. And since your section is compact, your nominal moment now will be equivalent to your plastic moment, which is 479.167. So applying the design strength criteria for LRFD and AST, we know that the strength is simply equal to PBMN. So this is 431.25 using the value of PB equals 0.90. And for the allowable stress design, your allowable moment or capacity is simply Mn over Phi, which is 286.926 kip foot or foot kips, where omega, the factor of safety, is 1.67. So considering now the next condition, wherein your beam is laterally supported within a length equivalent to 20 feet, and CB is assumed to be equal to 1.0. So we need additional information. We need these properties, not additional, but we need the properties shown here, and this was extracted directly from the table. Okay. So in other references or manuals or tables, LP and LR are automatically given. Also your X1 and X2 are included in the table, but for this particular reference that I use, LP and LR may be readily computed using a formula which is equivalent to this. Again, your 12 here is simply to to convert, okay, your uh, plastic breeze length limit or plastic length limit from inch to feet, because Ry is given in terms of inches. Okay, so this is in terms of inches. So we now have the value of the LP property equivalent to 8.689 feet. And for your LR, we can use two formulas. So this formula here is actually an old AISC formula, wherein x1 and x2 are computed on the basis of another formula, and FL is actually your stress, okay, stress limit considering a reduction on the residual stress. So this is the residual stress for road shape sections. So it's 10 KSI. So for built-up section, this will become 16 KSI for built-up shapes. Okay, x1 and x2 are given now on the basis of these two formula here. So plugging in the value of EGJA and SX, we get 3.016 cubed times 10 to the 3 KSI. Okay, and x2 is simply computed on the basis of this formula. Take note that we need CWSX IYGJ depth, and this is actually 0.002. Unit is in, I think, so this will be in inch square cube square. Okay, so we will check that later. So LR, using the formula for LR above, so this is now Ry x1 over FL, square root of 1 plus x to FL squared. So we can cancel out, yes, this is correct, no? So because this is FL squared. And your LR is in KSI. This is in KS, I'm sorry, this is to the 4th. So this must be to the 4th, because this is a K cube square over inch to the 4th. Okay, so this must be cube squared over inch square. Okay, so the correction here, and you have also here cancel Ry. Okay, so I think this is the correct units. So for LR now, we simply substitute the value of x1 and x2 as computed, and FL there given a while ago. Okay, so we convert it to, again, this is a conversion factor, okay, from inch to feet. So we get now 26.376 feet using the old formula. So for the video I shared to you on lateral torsional buckling, the new formula is given by this very long expression here, no? But the values for EJ, SX are just the same, and E, FY, only these three values were added. C, RTS, and HO are added on the basis of the formula. So for doubly symmetric shape, C is simply equal to 1. RTS, which is the radius of gyration of uh, the torsional element of the whole shape or whole section is equivalent to this formula, and HO is again uh, used to denote D minus TF. Okay, so if you're going to take a look on where are those special properties, so these are the added properties. So your RTS is simply the radius of gyration of the part of the flange part here, and including some part of the web, okay, which is equivalent to 1/6, okay, 1/6 of your uh, web height, okay. So this is the flange. So the RTS is actually the radius of gyration of this torsional section here. And also your D, or sorry, HO is simply the distance center to center of the mid depth of the flanges, or midline of the flange thickness. So this is simply your HO. And C is actually a factor taking into account what is the shape of the section. So for a doubly symmetric shape, which is a normal shape, normal condition, C is equal to 1. So using this formula, we simply plug in, although the equation is long, the computation is very easy. So direct input of such of the values here will yield now to a value equivalent to 29.27 feet, and you can use either value, and this value here is rather more conservative than this one. Okay, so conservative, and we are going to use this new formula, which is less conservative. So taking note of the comparison between your brace length and limits, we take note that your LP, which is 8.689 as computed earlier, is less than LB, which is 20 feet, and LR less than LR, which is 29.27. So if you're going to use the old formula, it still falls on this, no? But of course the computation will be a little bit different later because we are going to substitute LR using a different value. So take note that MP as computed a while ago is simply equivalent to 479.167 cubic foot, and this is in cubic inch. No? So since this are the value of your MR, so this is your residual moment, is in inch cube, I will be using my inch cube here, no? Or cubic inch here as my value for your MP. And using this interpolation formula, again I only need to plug in the values including CV there and divide it by 12. I can now get my moment, no, my nominal moment capacity in cubic foot, which is less than MP 479 380.931. So this is now your nominal moment, and for the design strength, we simply again make use of the PBMN for LRFT and your MN over omega for AST, so which is 342.838 versus 228.183. Again, this is now a more economical design and this is the more conservative design. Okay. Okay, for the third condition in the problem, we consider LB is 30 feet, so we're increasing now the end brace length. Therefore, the lateral torsional buckling behavior is now becoming more critical. And using again the same formula for LR, we compared as we have compared it a while ago on the B requirement. So this is now your C requirement, letter C. Okay. So again, we use the value of 29.27 feet. So this does not change because this is a property, So take note of that. It's nothing to do with the external condition. So this is not changing, Because this is a sectional property. So therefore, your LP now, what changes is the LB requirement. Your LP now, which is 8.689, is less than LR, which is 29, but less than LB, which is 30. Okay, so you are now on the slender side. So for your letter C requirement, you are now actually on this. Okay, so this is your LR, this is your LP, and your LB is somewhere here. Okay, so you are now on the not slender. We are using slender on compact section. So this is the elastic back lateral torsional buckling region. Okay, so we belong to this region. So our formula now becomes a critical moment formula in terms of FCR. Okay, so FCR is the critical stress that gives you now the critical moment. MCR equivalent to MN. So I just like to add here on the letter B requirement that our solution falls on the value of your interpolative function. Okay, so this is now your LP or sorry LR. This is your LP, and your LB is in this range, So this the embrace length, which is 20 feet, is now on this interpolative range. Okay, and this region is actually the inelastic lateral torsional buckling region, LTB region. Okay, so this is the region into which your interpolation function or formula is being now used. Okay. Okay, so to continue letter C now, we simply solve FCR on the basis of this formula. Again, J, C, X, H, O, RTS are just the same properties we have been using a while ago. So we just plug in all the values and then compute it, and we get your FCR to be 33.899. Of course, this is in KSI. Okay, so take note that the units must always be consistent. Multiply it by your SX and divide by 12 to convert it to cube foot. We have now 290.97. And the design strength for LRFD is simply PBMN, which is 261.873, and for ASD is simply MN over omega 174.234 cube foot. Okay, so that's it for this particular problem. Although the involvement of all the code provisions in terms of the additional properties and limitations are very much involved, So still the procedure is simple if you know how to deal with the pattern of behavior you are looking at, considering both compactness and lateral torsion buckling effect. So thank you very much for listening. I'll address your concerns after this video.